All right, hi everyone. So in the next couple of videos, I want to talk about two permutations of the particle in a box problem. And this is the first one. It's called a particle in a finite well. Described in Atkins 7D4, and it's very similar to the particle in a box. We have a one-dimensional particle, so is inside the box. The potential inside the box is 0. But what's different about the finite well is that the confining potential is not infinity, but it approaches some finite value. So there's now a finite potential holding the particle in. Mathematically, we would write it as follows: 0 inside the box, right, some finite value outside of it. And the first thing to calibrate yourself with is what happens classically. This is a relatively uninteresting question. What happens classically is that the particle just pings back and forth. If the potential is up here, it has this much kinetic energy, it just pings back and forth, same as particle in the box. We now want to solve this problem for a quantum mechanical system. And so our steps are going to be the same as always. We're going to start by writing the Schrodinger equation. H psi equals E psi. Given that the potential has these two different parts, we're going to break this up into two different halves. So first we're going to do inside the box. When I write the Hamiltonian operator, there's a kinetic energy term, d squared psi dx squared plus v psi equals E psi. Remember, we're inside the box here, so this potential is equal to 0. And I can write this problem as follows: d squared dx squared equals negative, negative 2me on h bar squared psi. Okay, I hope this looks familiar to you. Right? Inside the box, the potential is 0, and this is essentially the classic particle in a box problem. So the solutions to this, the eigenfunctions are exactly the same as particle in the box. Right? That is, psi n is equal to c1 e to the minus I kx plus c2 e, I should say this is positive and this one's minus I kx, where k squared equals 2me on h bar squared. Again, using that Euler's relation, I can write this as a combination of sine and cosine curves. It's an equivalent way to write it, different constant. And I could think about starting to draw this inside of the box. Now recall that in a particle in a box, we said that the wave function had to go to 0 at the edges because the potential was infinite. That is not true here. Right? We cannot eliminate these constants by requiring the wave function to go to 0 at the edges because the finite is potential. Can't eliminate with psi equals 0 at the edge. So inside the box, we get the same sine and cosine solutions, but it doesn't go to 0 because the potential isn't infinite. Second half. Outside the box. Again, a kinetic energy term, t squared psi dx squared plus v hat psi equals E psi. Outside the box, this is just some constant. So I'm going to write that as v psi. Right? If I rearrange this, equals minus 2me E minus V over h bar squared psi. Recall, or what's sort of assumed in this problem, is that the energy of the system is less than the potential. There is a greater potential so that it's confined inside the box. So this quantity is negative. Negative times a negative is a positive. So this whole thing is positive. And we get on the surface something which looks really similar to the particle in a box, traditional particle in a box. Right? The catch is that here, this is positive. In the particle in a box, we had a negative constant out front, and that introduced the imaginary terms, e to the ikx. In this case, because these constants are positive, the solution outside the box looks different. Rather than having an e to the ikx, we can simply get regular exponential decays, where this is the constant kappa, and this is defined as 2me v minus e over h bar squared. So outside the box, the wave function will simply exponentially decay. And we can use the properties of the wave function to determine CI constants. Right? It has to be continuous, it has to have a continuous slope, all of that stuff. I'm not interested in the math here. Instead, what I want to do is ask you some qualitative questions, or at least pose some qualitative questions to you. The first is, how do the energy levels of a particle in a finite box compare to those in an infinite box? What are the energy levels? And we're not going to derive a mathematical equation, but qualitatively, right, what I want you to think about, or what you should think about here, is the size of the box. You'll notice that the wave function has spread out. In some sense, the box has gotten bigger. And if the box has gotten bigger, right, the wavelength increased, its energy decreased. So in general, the energy levels in an infinite box are smaller, they're more closely spaced than those in an infinite box, because the box effectively got bigger. So it'll cause the energy levels to shrink. The second is a little more abstract, which is, what does it mean for the particle to exist inside the barrier? Right? I don't know. It's there. But it leads to this other interesting question, which is, well, what happens if my barrier isn't infinitely long, but instead has some finite length? Right? And I imagine a scenario in which that finite length is in fact less than the penetration of the wave function into the barrier. Right? What will happen? I'm going to post some videos that you can check out, but what you might imagine would start to happen is that if the wave function were heading this way and it impinged on the barrier, what you might imagine is that it leaks out, or leaks outs, I guess is that right? It leaks out. It can get through. And this is a crazy idea. Right? The system has less kinetic energy than the potential. Potential is greater. It impinges on the system and it gets through. It is as if I am rolling a ball up a hill. The kinetic energy is less than the height of the hill, potential energy, and yet somehow the ball gets through. So this has a specific name, which is called tunneling. Tunneling is a quantum mechanical phenomenon in which a particle is transmitted through some barrier, even though the kinetic energy is less than the potential. And what we're ultimately interested in is the probability of this happening. I'm going to skip ahead and give you the final equation, which is right here. The transmission probability through a potential barrier V of some length L is described by this equation. Note in this, L is the length of the barrier, not the length of the box. All right, let's interpret this. What factors does the transmission probability depend on? Well, it depends on epsilon, which is sort of the ratio of the kinetic and potential energies. So it will depend on the ratio of the kinetic and potentials. That makes some sense to me. It depends on kappa, right, which has, again, potential and kinetic energies. It also has a mass factor. And notice it's e to the negative kappa. So light things are more likely to tunnel than heavy things. And last is this one, L. That's the length of the barrier. And again, this is negative, so the shorter the barrier, the higher the transmission probability. So this all makes some sense to me. But here's the really interesting thing. Right? Which factor is most important? And this is non-obvious. But if you look, these potentials are either in the exponent to the 1/2, or they're here in a linear term. But the length is simply e to the negative L. So what this is most sensitive to is the length of the barrier. Right? It is a crazy, crazy idea. And one question you might ask is, well, does this really happen? Or is this some sort of thought experiment? How big is the effect? And I'm not going to do it in this video, but there is a worksheet problem which will have you think through this. It calculates a change in transmission probability as a tunneling barrier is decreased from 2 nanometers to 1 nanometer. And as you might guess, like, it's a really big factor. Okay? So it is important. And in fact, some people took advantage of this to develop a tool, which you might have heard of, called a scanning tunneling microscope. They won a Nobel Prize in the 80s for this. And essentially, the idea is that they're going to use this to map out the topography of an atomic surface. So you have some tip, which is brought very close to a surface. You bias this tip so that an electron, in theory, could tunnel from the tip to the surface. And this happens at some regular rate. If there's a little bump, an extra atom on the surface, this distance now decreases and the tunneling probability would shoot through the roof. So you get some experimentally measurable changes in current. And in fact, people use these to generate some images that you might have seen. Right? These are individual cesium atoms located on a gallium arsenide surface. Or this is one of the most common. It's a graphite surface where you can see the individual carbon atoms arranged in this honeycomb structure. So tunneling is an extremely important idea and is a purely quantum mechanical phenomenon. All right, we'll stop here and I'll tell you about the next problem in the next video.